Okay, this video is going to discuss a problem that we would have looked at in class the other day that deals with if we're given a bunch of information about different distributions, how can we tell if a normal model is appropriate to model these distributions? Very similar to the group task activity that we were given in class, except we're kind of given different information about each distribution. So the first thing to see is that we have 6 different distributions here, and they all have means of 100 and standard deviations of 20. And we're given information about the median, IQR, min and max. For some of them, in distribution F's case, we're given information about the 90th percentile and the 10th percentile. So we need to figure out if it's appropriate to model each one of these distributions with a normal model. So the way I'll structure this is I'll first kind of talk about what we should look at. And then we can kind of go through each distribution, see if it, if that criterion is met or not, and if it's not met, is that enough to knock that sort of distribution out of contention for being modeled with a normal model. Okay, so first thing we should look at is the mean approximately equal to the median? Because if we know that if the data are approximately normal, then we know we have symmetry in the data, and so we should check that for each distribution. And if a distribution does not have that to a satisfactory degree, we can knock that one out of contention for being appropriate to use a normal model for. So let's kind of go through each one. We can see the distribution A, the median is 100, so that one's all good. Distribution B, it's 100. Distribution C, the median is 80. That is one standard deviation difference from the median, and that kind of leads me to believe that distribution C would not be appropriate to use a normal model, just on this basis alone. Similarly, knowing that A and B, and actually we can see D, E, and F, knowing that those medians are all 100, which is the same as the mean, is not enough information to say a normal model is appropriate. We know that we can have data that are symmetrical but not normal. Okay? But if we know data are approximately normal, we know it has to be symmetrical. So distribution C is done. We don't have to deal with it anymore, regardless of what the IQR, the min, and the max are. Okay? All right. Second thing we should look at, perhaps, is let's look at the quartiles if we have that information, kind of similar to what we did on the group task. Is the IQR what we would expect from a normal model? One approach is to actually find what the quartiles should be when we have a mean of 100 and a standard deviation of 20. Another approach is to actually just find what the IQR should be. So I'm going to do that. So the first thing is I'm going to go ahead and find, and we've done this many times, what Q1 and Q3 should be, the z-score for Q1 and Q3 should be in a normal model. Okay? And we should know, and we've done this plenty of times, that if I find the z-score that corresponds to a 25th percentile, that'll give me the z-score of the first quartile, and a z-score which corresponds to the 75th percentile, that'll give me the z-score corresponding with that. So, and we've done this before. Bear with me for a second. If I do, and actually, there it is right there. We do inverse norm, 0.75, and inverse norm of 0.25. We shouldn't be surprised that those are opposites because we have normal models are symmetrical. And so we can see that this is negative 0.674, and this is positive 0.674. So the IQR would be the difference between those two. So 0.674 minus negative 0.674, which is really just 2 times 0.674. So I am just going to take and multiply that by 2. I know it's negative there. And we see that the IQR should be about 1.35 in a standard normal model. Now this These data are not the standard normal model. These data are a mean of 100 and a standard deviation of 20. So I can just take this 1.35, that's the number of standard deviations the IQR is, and I can multiply it by that standard deviation of 20. And what I will see is that the IQR should be approximately, if I do 1.35 times 20, 27. Okay? So if the data are approximately normal, the IQR should be about 27. Okay? I could have alternatively found Q1 and Q3 in the way we did in class, set this thing equal to 13.5 less than the median, and this equal to 13.5 more than the median, and solve those equations. But the point is the IQR is 27. Let's see if that's true. Okay, so for each distribution. Distribution A, it's true. Distribution B, it's true. D, it's true. E, it's not true. So that's kind of a knock against distribution E, that the IQR does not seem to be what it should be. It seems quite a bit too wide. So that may knock E out of contention for being modeled with a normal model. And then distribution F, we actually don't have information about the IQR. Okay, so right now I'm a little skeptical about distribution E. I've eliminated C, so we'll move on from there. All right, the next thing we should look at is we have information about the minimum and the maximum of each distribution. Let's see how far away the min and the max are from the mean in terms of number of standard deviations. Okay, because if the min and the max are too close to the mean, perhaps, let's say it's about 1 standard deviation away from the mean, that's it, that doesn't compute with a normal model, because we'd expect about 68% of the data to be within 1 standard deviation, 95% to be within 2, and almost all to be within 3. So let's see for each distribution how far the min and the max are. So we're going to compute the z-score for both the min and the max. So if I do that for distribution A, I find the z-score of the minimum, and I'll just do this real quick. I get 75 minus 100 over 20, and I see that that is negative 25 over 20, which is negative 1.25. I can do the same thing for the max, and actually it's symmetrical, so that z-score for the max is 1.25. So that tells us that all of the data are within 1.25 standard deviations from the mean. That doesn't really compute with a normal model. We should have data further away. We should have about 5%, or in this case, 5% of the data points should be outside of 2 standard deviations. We have all the data within 1.25 standard deviations. So that's going to knock out distribution A. Distribution A is likely not a good candidate to be modeled with a normal model. All right, so we've eliminated A, we've eliminated C, we've eliminated E, really, because that IQR is just too big, so that leaves B and D. Okay, so I'm going to pause it. I'm going to write down the computations for finding those z-scores of the min and the max for B and D and F, and we'll see how it works. All right, so now I went ahead and computed all these z-scores that correspond to the min and the max of each distribution. And what I can see is that in distribution B, all of the data are within 3 standard deviations of the mean. And that should make sense, because we would expect nearly all, or 99.7%, to be within 3. Well, all are within 3. So that kind of makes sense. So distribution B right now is looking like a strong candidate to be modeled with a normal model. In fact, we've investigated all the information here. So if I were a betting guy, I would say distribution B is approximately normal. Same thing happened with E. They have the same min and max as B. This is F. This is not E. Okay, you find those z-scores, you get that all of the data are between -3 and 3 standard deviations. And so distribution F is looking good. Now, we still haven't evaluated these percentiles for distribution F. Now, distribution D. If you look at that, you see that all of the data are within 5 standard deviations of the mean, which certainly makes sense. But 2 of the points, the min and the max, are both 5 standard deviations from the mean. It's very, very, very unlikely in a normal model to have data that far from the mean. And because we have 2 data points, both the min and the max, that far from the mean, it seems like that D is not a good candidate for a normal model. Now, we don't know for sure, because perhaps it's just an anomaly that there might be a data point at 0 and 200, and then all the rest of the data are closer to the mean, like within 3 standard deviations or 2 standard deviations from the mean. But the fact that I have 2 data points that far from the mean tells me I don't know that a normal model is the best model. I would actually want to see more. So I'm going to knock D out of contention here. All right? So we've decided for A, D, E, C. We don't think a normal model is appropriate for those. B, we do. Okay? Let's look at F, and let's look at the last piece of information that we have not used. It's those percentiles. All right? So very similar to what we did with the quartiles. We can find the expected z-score of the 90th percentile and the 10th percentile, and then compare that to the actual z-score of those values. Okay? So I'm going to look at distribution E. All right? So let's look at the expected of the 90th percentile. All right, and I have 3 minutes to finish this. So that's going to be corresponding to finding the z-score corresponding to the area of 0.9. So I'm going to put in the calculator inverse norm of 0.9, and I get 1.28. That tells me that the 10th percentile should be negative 1.28. All right, so now let's find the actual z-score. So we're going to do 115 minus 100 over 20. Okay, the 90th percentile is 115. The mean's 100. The standard deviation is that. So we get 15 over 20, which is about, well, 2/3, 0.67. That's the actual z-score. So what I can see is that the 90th percentile is much closer to the mean than it should be. It should be about 1.28 standard deviations from the mean, and it's actually 0.67 standard deviations. So that's knocking out distribution F. So I don't think a normal model would be appropriate for that. Distribution B looks like the best candidate here. So if this is like a lineup of a bunch of criminals and we're trying to pick out the one that's normal or approximately normal, distribution B would be the one that I would pick. I'm also posting all this work so that you have it, but please spend some time understanding this. There's a lot of concepts that are nestled in. Thanks for watching.